Okay, hi everybody. Welcome to this ninth week of BIOB20. Maybe we're going to start by asking questions and going again over what we've seen in the previous weeks. And I know that, Amira, you had a question that you wanted to ask about tutorial 8. Do you want to ask it now?
Yeah, my question is really about using that Microsoft test. I was wondering if you could just use the median values. I didn't really understand why we were using rank to determine like whether there's a shift.
Yeah, so the question is why we're using the ranks to determine whether there is a shift. So what you're saying is that we could just use the median. For instance, I could say that I'm taking my favorite function like onorm5 would be this sample, and another one that would be onorm5 plus, I don't know, 300. And is that not obvious? Then when you do median x and median y, well, there's a difference of 300. So that's what you mean, that we could just take the median between the two samples, so you had a... Yeah, so it's a very good point, and it's a very good question. Sometimes you'll see that the Wilcoxon-Mann-Whitney U-test is called a test for the median. So that's false. That's not a test for the median. I'm not sure that this exists, but still it means something. So it means that when people imagine that this Wilcoxon-Mann-Whitney U-test, when the median of two samples or two populations is the same, the statistic should be 0, and when the medians start to get apart from each other, when they're different, then the statistic should go high and we should reject the test. So it's not true. The Wilcoxon-Mann-Whitney U-test is not a test for the median. You can easily craft examples that have the same median and that are rejected by the Wilcoxon-Mann-Whitney U-test. I'm actually going to do it right now so that you can understand what I mean. It's quite interesting. So when you have an exponential distribution, so you take an exponential distribution, let's say with 100 numbers like this, the exponential, remember, it's got a tail on the right, like it's blocked at 0, all the numbers are positive, and then it's got a tail on the right. So what is the median of the exponential distribution? So 0.6, something like this. So we're going to say that we're going to make one sample which is taken from a shifted exponential distribution such that the median is 0. Okay, so the sample x is going to be a sample of 1,000 numbers, let's say. Okay, oops. So here I've got my 1,000 exponential numbers, and I'm going to say that x is equal to x minus the median of x. So now the median of x, by construction, I crafted it to be 0. But if I say, what does the histogram look like? What does the distribution look like? You see, this is a distribution that's typically exponential, but now it doesn't start at 0. It starts at -6, 0.6, something like this. Let me add a couple more ways. So the distribution looks like that. And I'm going to make another sample that I'm going to call y. Okay, again exponential. But what I'm going to do is I'm going to flip it. So y, actually, what I should have done from the beginning is to say this is minus the exponential. So now it's going in the negative direction here. So if I do the histogram of y, here you can see that this one is reversed, and it's going in the other direction. And I can do the same. I can say that y is y minus its median. Okay, so the median of y is 0. By construction, I crafted these examples so that they have the same median equal to 0. So now if I do Wilcoxon test, Wilcox test on x and y, they have the same median, and the p-value is 10 to the minus 15 here. So Wilcoxon-Mann-Whitney U-test tells you I'm pretty confident that these two things, I mean, if you believe that this is a test for the median, you'd interpret like they don't have the same median, but that's not true. This is not what the Wilcoxon-Mann-Whitney U-test is for. So what's going on here exactly? It's the fact that the Wilcoxon-Mann-Whitney U-test, like pretty much all the tests that we've seen so far, the null hypothesis is not that there's no difference between the mean or between the median, or between any statistic that you can measure on it, is that the two distributions are exactly identical. It's the alternative that says the difference is a shift. Like the only difference that you're allowed to envision in this test is the fact that the two samples are a shifted version of each other. Here it's not the case. Okay, the samples are like very asymmetric. There is these two tails going in opposite directions. In that case, the Wilcoxon-Mann with Neyu test freaks out. It doesn't know what to do with this. This is neither in the null hypothesis case nor in the alternative hypothesis case. So it's really important to understand that there's no such thing as a test for the median that really cannot exist. The only thing that you can do is to say the null hypothesis is that the samples are exactly identical, they have the same exact distribution, and then you work on the alternative hypothesis side that says, I will reject when that happens, but you're not saying what you will do when other things happen. When you think about the t-test, people say it's a test for the mean. It's the same thing. There's no such thing as a test for the mean. It does not exist. What you're saying is that the distributions of the two samples are the same and they're both Gaussian. And what you're allowing to happen is that, again, there's a shift between these two Gaussian distributions in the alternative hypothesis. So this is why if you hear sometimes the Wilcoxon-Mann with Neyu test is a test for the median, this is false. That's not true at all. If it's a test for something, it's a test for the Hodges-Lehmann statistic, which is something quite complicated, but nothing interesting here. So let's go back now to the question, which was, why don't we just use the median to separate the two samples? So you need to get a statistic for the distribution for the median. And that's not easy. Like really, depending on the shape of the distribution, etc. Nobody has ever come with a good idea of how to get a statistic for the median. You can have a statistic for the mean, okay? And so like we can use the replacement, which is the effect size, divide the mean by the standard deviation, and that kind of gives you a Gaussian distribution if the sample is large enough. But for the median, you would need to make more assumptions about your initial distribution. So that's why you can't really have a test for the median that is so generic. But you can have a test for the differences of the ranks, because then you can find the null distribution. The only thing that we've been doing so far, it's just spending almost all our living time here trying to find null distributions. This is really the effort of making these tests work. Either you can find a null distribution or you cannot. If you cannot find a null distribution, your score could be awesome, have the best properties in the world, but you can't make a test with it. So the answer why we're doing it this way is because it's kind of the only idea that came out there for having something that you can know the distribution of. And the median is just too generic. The example that I gave you here says that, yeah, even when you have exactly the same median, you can have some tests, some samples that are obviously different, and probably should reject them. They don't have the same distribution. You should reject the null hypothesis in that case. Right, so the short answer is just that we can't. Like there's no test for the median. There's no idea what the distribution of the median would be in very vague terms of the null hypothesis. We have to do it with what we have, and that's the ranks, the sum of the ranks. Right. Did I answer your question, or I sidetracked too much? All right. Other questions? Online, do you have questions? Apparently not. So we've seen the notion of power, which is extremely important in statistics, especially when it comes to statistical testing. So for power, what do we need? And so how do we define power? The definition of power in statistics is extremely simple. That's the probability of rejecting the null hypothesis. That's really all it is. So your power at when the null hypothesis is true, and there's usually one case when the null hypothesis is true, your power is your level. That's 1% if you work at 1%, it's 5% if you work at 5%. So in that case, the definition of power is pretty straightforward. If the null hypothesis is false, well, it depends. The power is a function. So that depends on what exactly is the reality. So that's something that goes from reality to giving a probability of rejecting the null hypothesis. And ideally, what you want for a statistical test is that when the null hypothesis is false, as soon as it is false, basically, you would like to reject it. And so you want the power to be as high as possible. But when the null hypothesis is true, you don't want to reject it. So you want the power at that particular value to be as small as possible. So when you make these power curves here, So you've got on the y-axis the probability of rejecting the null here. Okay, so that's the prob of rejecting the null. And here there would be, for example, a difference. And we're just going to write delta to say how different is the reality compared to your null hypothesis. So you have here at 0 what should be reality, like this is your null hypothesis. And as you're going to the right here, the difference increases and the reality is no longer your hypothesis. The point that you have, I'm going to switch color here. Okay, let's take here this one. The point that you have here is set, you choose it, that's the level. So that's the probability of rejecting the null when the null is true. So you accidentally make a mistake, you reject the null, and we set it to 1% in our cases. So this one is set, and test with a good power will rapidly go up like that. Okay, that's a test with a good power curve. And if you have a test with a less good power curve, then anyway, you have to start here. All the tests, if they're well calibrated, they all start at the level, and then it could go something like that. And so if you've done the exercises as it should, you've seen that in some cases, the Wilcoxon-Mann-Whitney U-test was more powerful than the t-test. And in some cases, it's the reverse. So there's no test that wins all the time. And so that depends a little bit on the initial distribution, basically. And so when you have something which is symmetric, usually the t-test works better. But when your distribution is asymmetric, the Wilcoxon-Mann-Whitney U-test has an advantage there. It's much more able to pick up differences, even smaller shifts that the t-test is not able to pick up. So that's what we, basically that was the upshot of what we've seen in the tutorial 8. We're going to go back to these ideas of rejecting the null depending on the conditions, etc., but not today, more in the next class. Is that okay, this idea of power of a test? Do you guys get the idea? So that's something that you do when you start a clinical trial. More and more also for people who work with ethics, I mean, not work with ethics, people who have ethical considerations in their work. For example, if you're going to sacrifice mice for your research, you are asked now by the ethical committees to say, you have to give us the power curve of your test before you even start killing mice. You have to show us that you're not throwing mice, just, like killing mice until you get the proper effect that you're looking for. So you have to say, what chance do you want to discover what? Based on that, you make your power curve. You see whether you have enough power to find what you want to find, because the only way to increase the power very easily is to get more data. But when getting more data means killing more animals, ethical committees say, you have to show us that you're not just doing nonsense. You have to show that you have the power to find what you want to find with the number of mice that you're requesting to kill. And you can get an approval, or you can not get the approval. People will say, no, like your protocol is just too silly. You would need to kill way too many mice, don't do that. So power curves are actually quite important. Before you start on something, you have to know whether this is a good idea, whether you're going to have problems finishing your study, or whether you'll be able to do it. So if there's no questions, we're going to change topic. And today we're going to speak about the chi-square test. And the chi-square test is a very interesting test. If anything, because many of you, I'm pretty sure, have seen it before. And many of you, I think, have built the wrong conception of statistical test just because of the way the chi-square is done. And we're going to see a little bit kind of what's wrong with the chi-square test. And there's nothing wrong, but I think this is one of the reasons why so many people really had this impression that you can use the data to make your null hypothesis and your null distribution, because that's the way it looks like in the chi-square test, when in reality, this is not exactly what happens. So we're going to try and demystify a little bit this, and this is exactly the point of tutorial 9, is to go with you through the chi-square test so that you can understand that at no moment in the chi-square test is the data used for anything else than computing the observed statistic. It's actually not used for the null distribution, even though it looks this way. But before this, we're going to to talk about contingency tables. So what's a contingency table? Can anyone tell me? Anyone knows what's a contingency table? Association between the variables. Yeah, between two variables. So for example, if I've got X and Y and I've got a scatter plot, is that a contingency table? right? So exactly. So that's categorical variables. So first, that's the table. So you're going to have a typically a table. I think everybody knows what the table is when we're talking about statistics or mathematics. So you have a 2x2 table here, and you have categorical variables. So typically, the best categorical variable in the world is yes and no. When it's 2x2, like you would typically have something yes, something no, versus something else yes, something else no, right? So for example, is a domestic yes, domestic no, is a woman yes, woman no. So and many things can be put inside a 2x2 contingency table. And typically you would do some sampling in this contingency table, and you would fill in the numbers like that. So here 1 and 3 again, something like that. So you say we've sampled 4 people, 8 people in total, I meant. And so 4 of them had this category here, 4 of them had the other category for this variable, and so on. Okay, and 3 had the double yes, 3 had the double no, etc. So it's just a way to count categorical variables. And when you think about it, when you have categorical variables, it's pretty hard to have anything else on the contingency table. Right? You cannot add categorical variables together. You cannot modify them. You cannot do anything. The only thing you can do is count them, count their frequency. And once you have these frequencies or these total occurrences, well, you're kind of done with pretty much every modification you can do with it. So now, what kind of questions can you ask that's interesting with these categorical variables is, well, as usual, we have only one question so far, is all these things just silly number that have been put at random in the table. And if you want to ask that question, what do you mean by silly numbers at random? We'll see that this is quite important here. So we're going to start not with the chi-square test, but with Fisher's exact tests. So Fisher, Ronald Fisher, is a hero of statistics, because he kind of invented statistics, actually. So the guy did pretty much everything that is now in the modern version of statistics. The only competitor he has is Carl Pearson, who was kind of older than him, quite a bit, who has done a lot of things. And actually, the chi-square test was invented by Carl Pearson. But otherwise, pretty much the modern version, what we're studying now, it's all been made up by Fisher, mostly. And so Fisher, in one of his textbooks, explains one particular anecdote that happened at his home, is that he's got this friend, Muriel Bristol, said, I can tell the difference by taste when people pour tea in my milk or pour milk in my tea. The taste totally different. And Fisher was like, no way, you're bluffing. And she said, no, I can totally tell. So Fisher just one day, just like, for the fun of it, pours milk in the tea and says, so what is it? And she says, it's milk in the tea, that's obvious. So he thinks to, well, maybe there is something. Maybe this person is actually able to tell a difference in taste when the tea is poured in the milk or the milk is poured in the tea. And being a scientist, he says, after all, I don't know, but being a statistician, what I can do is I can make a test for it. So he comes to her and he says, well, because you say you can do this, this is what we're going to do. I'm going to prepare, secretly, I'm going to prepare 4 cups where I'm going to put the tea first, and I'm going to prepare 4 cups when I'm going to pour the milk first, and you're going to have to guess. And so then Muriel Bristol kind of taste, and she says tea first, milk first, etc. And in the end, it came like that, with that particular table here. Okay, so I'm going to remove the labels. We're going to change them up. So I'm going to use M and T for milk first and tea first. So here, that's the truth. Either you have milk first or tea first here. And I'm going to say here that's the reality. So that's the first categorical variable. And the second variable is what Muriel Bristol said. And so here, this one, she said milk first 3 times out of 4, and tea first, well, she also got it 3 times out of 4. And so this is MB says, here, Muriel Bristol says. So far, so good? Right, so that's typically a place, this table, where we record the success rate of sorry, of someone at a particular challenge or something like that. And now the question is, okay, Muriel Bristol has done her work, now it's Fisher doing his. How do you approach something like this? How do you test whether this is an incredible performance or whether that's kind of an, a mediocre average performance? So she's performed more than the 2222 that you'd expect when a person says completely at random, but this is not a perfect score. So how would you study a problem like that? How do you start? And you don't have to use the means of Fisher. You're allowed to use everything that we have nowadays. Go ahead.
Wait, sorry, just to clarify. So the numbers, the numbers are saying that there's 3
It's a good question. So how do you interpret that? So the reality is that here, 4 times Fisher put the milk first, and 4 times you put the tea first. Right? So like it's 4 and 4 here, but it doesn't tell. It doesn't tell, of course. And but he says to Muriel Bristol, that's what I'm going to do. So she knows that it's 4 plus 4. And her answer was like, it's those 4 and those 4. And she got 3 out of 4 correctly guessed with milk first, and also 3 out of 4 correctly guessed with tea first. And so here, it's also 4 and 4 here. So now the question comes, how is that better than chance? Is she really psychic? Or I don't know how to call it. Can she really tell? What do you guys think? How do we even start a problem like that? Right, exactly. So always, we're always assuming the one thing that we can model, there's one thing only, it's chance. The thing that we cannot model is psychic powers and like being able to discern things that other people cannot discern. But we can make a certain expectations about what we expect if the person is just lucky. And we could say this is more than luck or this is not more than luck. So that's what we're going to do. And the question is then, how do you resample something like this? What kind of randomness happens here? And the important point to understand is that Muriel Bristol knows that there are 4 plus 4. So for example, she would never say, we cannot have a table that looks like that, right? Where you have here, it be, she says, I don't know, something like 8, 0, 0, 0. Right? That's just not possible because we know that there are 4 and 4, and she knows, and she's also going to always make sure that in her total answers here, it's 4 and 4 here. She's not stupid. She's not going to give 3 and 5. She was told it's 4 and 4. So in reality, there are quite some constraints on these tables here. Okay, we cannot just put any number that we like in it. So we have this idea that if we want to understand exactly how random these numbers are, we need to randomize them, but we have this constraint. It's like, because she knows and she's not stupid, she's always going to give an answer that has 4 and 4 here. What's the chance that under that constraint, you get a table that looks like that? All right, so far so good? Like this table, she cannot give that answer. Like it's just completely out of reach compared to the problem. So we need a way to sample things this way. And so one particular way that we can do this is we can recode the data that's in the table here. Okay, we're going to do it with, for example, a data frame here, where we're going to say that that here is a data frame, and we're going to say that the first variable is the reality. Okay, and the second variable is MB says here. So we're going to have 2 columns. The first is what is it in reality, and the second is what does Muriel Bristol say. And so the reality is that here, if we look at this particular table here, there are 4 cups that are milk, 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 okay, 4 times milk. And then we also have T, 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 T. So that's the reality. The first 4, let's say, or milk, the order is irrelevant for now. The next 4 are T. And so what does Muriel-Bristol say? I'm going to make some space here. Well, she says that also the order is irrelevant. You'll see in a second why. But let's say she says milk, 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 and what's the next? Tea. Okay, like she makes a mistake. So like the first 4 were milk, but then she makes a mistake. The next are like tea, that's correct, tea, correct, tea, correct, and the next is N. She makes another mistake. So like the data looks like this. Okay, so the reality is it was 4 milk, 4 teas. She says 4 milk, 4 teas, but like there's one mistake here and another mistake here. So I'm just recoding the data. And what's really nice is that there's this function called table in R that computes the table exactly like I want it. So except that it has flipped reality and what Muriel-Bristol says, but that's exactly the same data. Okay, so the function table is really handy in that case because it allows you to go from categorical data in the data frame and then directly build the contingency table with it. It could be called contingency table, but they just called it table. Really handy way. So the point now is that if I want to recreate the constraints that these things is completely random, I can just move around the columns. I hope you see this, that if I'm just shuffling around the position of the column reality and the position of column MB says, I will always have 4 M's and 4 T's no matter what, except that now they're going to be not linked anymore. So they had their initial linkage here, which is the way they were in the data. And hopefully for this person, like the linkage is not random, but I'm going to break that linkage and then start to shuffle around the labels. So what I can do is to say that reality here. So remember that this is the way I access one column of the data frame is how do I change the order of a vector? Do you guys remember? Just if I say sample with that vector, then it's going to just shuffle the order completely. That's reality. So now here's the data. So these labels here have been completely shuffled. Right? I can do the same for MB says. And I hope that by now you agree that this particular version here of the data is random, is one possible random outcome of picking at random under the constraint that you're taking 4 plus 4. Okay, like whichever original linkage was present, I've completely broken it by taking this sample. And when I do table here of that, am I going to get the same matrix? Probably not, 2, 2, 2, 2. But the point is that the total number of M horizontally is going to be 4. The total number of T horizontally is always going to be 4 because they're the one from the column reality, and there's 4 plus 4. I'm not changing that number, I'm just changing the position. And the same will go for the columns, like 4 M's in column, 4 T's in column. That's not going to change because I just shuffled them around. Okay, so far so good? So that's one way to think about the possible way that Muriel-Bristol would be solving this problem if she had no power. She'd just be saying, well, whatever, taking this one, these ones. She just makes sure that she answers something in the end that has 4 and 4. But in reality, she's putting the labels at random over the cups of tea that she's given. Okay? So now what I can do is I can reshuffle that many times. That's pretty easy. But I need a statistic. So any idea which statistic I could use in this case? Ideas around. So it doesn't need to be very complicated in reality. I can just take, there's an idea. I compute expected counts. But that was somehow different is from expected. Yeah, okay. So we could take the difference with the, let's say the dull null expectation, which is this one, this matrix 2, 2, 2, 2. We could compare the difference with that. So one thing is that if we do the difference, okay, the difference on average is 0. Okay, you see why? Some numbers are going to be higher, but it's going to be exactly compensated with the numbers that are lower. So if I do 2, 2, 2, 2 minus 3, 1, 1, 3, and then I sum everything, I'm always going to get 0. So that's not a very, very good score. Yes. Okay, so if we're about to do something like this, at least we have to count everything positive. So either take the absolute value or take the square, something like that. So here you take the square. If you take the absolute value, you'd mean that whenever you make a difference of, for example, 2, that'd be much, much worse than a difference of 1, because the square would give you 4 in terms of how much you pay for that mistake. All right, so we could do things like this, but we're going to do something much simpler. We're just going to say that our statistic is going to be that cell here. That's our statistic here. That's 3. So why does that work here? So if I'm putting a 2 in that cell here, okay, how many other cells of the contingency table are determined if I just decide to put a 2 here? All of them. Okay, so that determines everything. If I put a 2 here, my sum has to be 4, so here there has to be a 2. That's like Sudoku. And so here, if I got a 2, then the sum has to be 4, so that's a 2 again, and here there's a 4, so that's a 2 again. So in reality, I just choose one number, and that determines the whole table. So I just need to give one number, and that's the number of successes that she has in that particular cell. If she's got a 0 here, then determines everything, 1, 2, 3, or 4. So in reality, there are only 5 possible tables, 0, 1, 2, 3, 4. Okay, with this constraint, it's actually very, very much constrained when you say that she knows that there are 4 and 4. You have only 5 possible tables, not 1. It feels like there were many possibilities, but in reality, just telling her that it's 4 plus 4 restricts tremendously this, like the freedom of the problem. There are only 5 possible outcomes. So how do I extract then a particular number from a matrix? I think it's something that I kind of forgot to mention, the fact that we can use matrix notation actually. So we've seen this for vectors, but when things are squared, this is the index of the row, this is the index of the column. So here, of course, all the numbers are 2, so it's not a very good example. We're going to resample something else and then see what the data looks like. Okay, here's a good example. So when I take this, I get the 4. It's this one, and again, it's the MM. Okay, first row, first column. Right? So that's the way I can do this. I can just take my data, sample it, and then plug that particular value here, and that's really my statistic. Super easy to compute statistic. Anyway, the higher it is, the more Bristol has scored. She has managed to guess what were the milks and the tea, and the lower it is, and then the lower she is. So we have to decide whether we're interested in her being extremely unable to do that, like much, much, much less good score than by chance. But that's another question. So how to approach this? Then we will need to run a for loop, and then in the for loop we sample the columns of that, and we extract one particular cell, and it shows the top left like this. So let's do this. I'm making my for loop. Let's say I'm going to make only 1,000 or something like this. So the statistic here is going to be 1,000 pennies. I'm just initializing with nothing, remember? And I say for I in 1 to 1,000. I'm saying that the statistic, the ith one is, how do I do this? So it's going to be table that here, keeping this thing at position 1, 1. But I need to shuffle it first before I do that. So does that make sense for you that I need to shuffle only one column? I don't need to shuffle both. Does that make sense? Yeah, because like once one is random, then anyway, there's no linkage anymore. So I just need to do this with the reality first, let's say. So let's say that the reality is the sample version of it, sample. So I'm shuffling reality, and then I'm computing the table, and then picking the top left entry and putting this in statistic at position I. And I will run from 1 to 1,000. So I'm going to fit in my vector I as things go. It just takes a bit. By the way, OR is an extremely slow language in many ways. And the for loop is just ridiculously slow compared to other languages. So it's something that is quite noticeable when you use other programming languages, which is why if you have a better way than a for loop, do that better way in general, unless you have plenty of time, of course, it's not a problem. So here, let's see the statistic. Okay, so I got plenty of 0, 1, 2, 3, 4, and that's it. Like I can get only these numbers here, and I can do the hist of the statistic. And of course, like it's a very silly histogram because it's got only 5 possible values. And you can see that the 3 and 4 here, that be the p-value, it's not rare at all, actually. There were only 5 cases anyway. So in reality, getting as lucky as getting 3 or 4, it's absolutely not rare. You know, it's something like 25% or something like this. So we can compute it. So how often is the statistic greater than or equal to 3? Oops, the sum of it. 256, right? So that's super, super frequent. 1/4 of the cases, people get 3 or more when they choose completely at random. So in that particular case, what's really weird though is that Fisher concluded that she had a superpower. And he said, like, dude, like you come that far, you invent the statistical test, and then at the very last minute, you drop it all, say, but yeah, no, I'm sure she does. Like this is the thing. I'm not sure if it's true or not, but like the legend says that he did believe that she had a superpower. I'm not sure why he would need statistic then. Anyway, so does that make sense for you, this way of thinking about the problem, right? So I've got this, this constraint, 2 rows, 2 columns. And so if I know the number of yeses and the number of no's, then I can shuffle the statistic this way and then decide that, well, not impressed.
When we ran the for loop,
Yeah.
we also shuffle every single time when we get a super statistic.
Yeah, exactly. So you need to resample at least one. If you resample none, of course, you always get the same data and then nothing happens. But if you resample one, like you're just breaking the linkage between these between the two. So if this is random, well, you don't need to randomize that. You can if you want, but that's a bit of a waste of time, waste of CPU time. It's already randomized.
If we have a table that was say 3 by 3, we would be able just to take the first one.
Absolutely.
Statistics.
Yeah. Exactly. If it's a 3 by 3, then we'd not be able to use such a simple statistic, like because it would not determine all the cells of the matrix. Exactly. So that's not a perfect test. That's not a perfect idea that we have here. We're just playing with 2 by 2s.
Are we gonna look at
what?
Are we gonna look at how to do it with?
Sure, of course. So that's actually one of the questions of the tutorial. But here, so the point is that Fisher's test works only for 2 by 2. And so like he had an idea, which is not this one. He didn't have access to computers. This is much earlier. So he solved the problem in another way. But anyway, he kind of stuck with 2 by 2 matrices. This happened much later than the chi-square test that was invented in 1900. And so like he decided to invent a specific test for the 2 by 2 case. But this is not the only case of interest, of course. All right, so far so good. So how did Fisher think about the problem? Of course, Fisher did not have access to a computer, could not randomize the stuff, but he was really smart and he had a proper British education. So he was thinking of every problem in terms of white balls and black balls. So he said, isn't that analogous to actually having 4 black balls in an urn, 4 white balls in an urn, and then Muriel is kind of, drawing just 4 balls, and then she says, look what I got, like 3 white balls and 1 black. So like the numbers of white and black balls that she would get in the inner draw without replacement would actually be her score. So that's the way he thought about this. Does anyone know what's the name of the distribution when you're putting black balls and white balls in an urn and then picking them like this without replacement? It's the hypergeometric distribution. So if you remember last week, the group work, you had a problem like this, like 50 white balls, 50 black balls, and then you draw 50, what's the chance that you get as many white balls as black balls? So most of you have answered that problem by doing a simulation, but there's at least one person, or maybe more, who has solved it by just asking OR what's the answer, because OR has got a function to solve exactly that question. So that's the function d hyper for hyperdistribution. So density distribution function, quantile function, and random, blah, blah, blah. So this is really the setup where you put plenty of black balls and white balls in an urn, and you draw them without replacement. So if we look at this, there's the parameters x, m, and k. So x vector of quantiles, or representing the number of white balls drawn without replacement. So we're counting the white balls. M is the number of white balls in the urn, n is the number of black balls in the urn, and k is the number of balls that we draw at random. So the person solved that problem by saying m equals 50. We have 50 white balls in the urn. K equals n equals 50. We have 50 black balls in the urn. We draw 50, so k equals 50, and x was 25 in that case. And that's the answer to the problem. So there was actually a single line answer to that problem. You didn't need to go through the process of resampling. Another way was to actually count the possibilities. You didn't choose like 50, choose 25, etc. Like there were multiple solutions. As usual, everything we do, there are multiple solutions. But the one that is the most like textbook solution for those who know their probability distribution was to use d hyper. And definitely Fisher knew his hypergeometric distribution, he even had the capacity to compute it. So that's what he did. Let's think about it. So if we say that let's say when we are going to count the white in general, that's the default. And because we're counting the success, every time we draw a white ball from the urn, it will count as a success. So what is M, N, K, and Q in that case? So M, the number of white balls, how much is it? 30? No, like in the case of Muriel Bristol doing her. Okay, so there's 4 white balls. Okay, she cannot get more than 4 white balls. The number of black balls, also 4. Okay, and then so the way this works is that the white balls, I said it wrong, I think. The white balls would be, for example, the milk first, okay, and the black balls are the tea first. And so she draws 4 balls at random that she designates as the milk first, okay? And so if the 4 balls are white, then she has correctly designated the milk first, all the milk first as milk first, and she gets the best score. And of course, she has not designated the other one, but they fall in the category T first, and so she gets them as well. And K, the number of balls that is drawn, it's 4. Okay, so let's do this. So that looks like D hyper. So I always have trouble remembering what is what. So M is the white balls, that's 4. N is the black balls, that's 4. K is the number of balls that we draw, that's 4. And we say that she gets 3. And so that here is the probability of getting 3 out of 4 correct. And if we count 4 here, it's like that. So the correct answer would be this, the probability of getting 3 and the probability of getting 4. So that's 0.24. Remember, we had drawn 1,000 samples, so it's quite close to the simulation. If we had drawn a bigger sample, we'd get to the same value. Okay, so that problem here can be solved either by resampling the labels in the table. So you really recode everything and then say, I'm putting every individual here as a function of 2 columns because we have 2 columns of interest. And then I'm using the function table to recreate the table. Or I can make it in a much more formal way by thinking about it in terms of white balls and black balls. So far, so good? You get the same results. Either you know your probability or you are able to just resample using a computer. Right, any questions so far? All right, so now we're going to go to the more interesting case where Fisher would have been evil and he would have not told Muriel Bristol there will be a 4 tea first and 4 milk first. What is he gonna do? He's going to flip a coin and say, if it's a head, I'm going to serve a tea first, and if it's a tails, I'm going to serve a milk first. But I myself, I don't even know how many milk first and tea first there will be. Okay, so what does change here in that particular context? How are we going to be able to solve that problem? How do we start? Okay, you guys understand the difference now? Is that there were only 5 possible tables when we put the constraint that we told the person how many milk first and how many tea first they are. But if we're not telling anyone because we don't even know we're going to flip a coin, there are many more possibilities. So how do we even start addressing that problem? Yeah, exactly. Well, that's because that's the only thing we can do. We're just going to randomize stuff, etc. Another question is, how are we going to randomize this contingency table now? So maybe we can think in terms of that matrix. Okay, it's kind of hard to think of how to put numbers in a contingency table, but when you say, yeah, of course, like one thing that is a constraint is that there are 8 cups in the end. And so how are we going to put the labels in this data? How would you proceed now? Go ahead. Yeah. Yeah, exactly. So we're just going to use the sample function with replacement, basically. So that's all we're going to do. All right. So we're going to say that here we have the right numbers, but we're going to say we say sample, for example, m and t here. So when I just do that, I get m, t, o, t, and m. But I can say size equals 8. Right? Remember. So that, of course, does not work because I have to say replace equals true. And now, well, I get exactly the same thing as flipping a coin and allowing myself to get multiple times m and t. So the number of m's, for example, what is the distribution of the number of m's now? Before it was a constant, it was 4. Now it's not a constant, but what's the distribution? Anyone remembers? Binomial. Okay, that's a binomial with probability 1/2 and n equals 8. So one way to sample it, here we either do or binom and then sample really the number that we get, or if we want to sample m and t because we want to remember the labels, we do it this way. So what I would do is this, that reality would be that here, we sample with replacements, size 8, that's a constraint, and we do the same for MB says. This time we need to do it both times because we assume that Fisher every time flips a coin to know what he serves, and that Muriel Bristol, equally clueless, also flips a coin to say, I'm going to say T first or milk first. So I get something where in that particular example it's pretty clear the constraint has been fairly relaxed now. We know that on average there are 4 and 4, but in one particular example it's no longer the case. And once again, if I'm interested in getting the table, then I do it this way. And now, well, obviously we don't at all have the constraints that we used to have. Okay, and does that make sense? Okay, we're making progress. So now, okay, can I use my favorite score here to say that one cell here, does it determine the rest? No, it doesn't determine anymore. Now that we have lifted the constraint of knowing the number, like the sums on the rows and the sums on the columns, that doesn't apply anymore. So we cannot use that score anymore. Okay, it's kind of bad luck. But still, before we know what to do, maybe let's look at one cell in particular. So we have said that this is a binomial distribution here. Okay, and what is the probability distribution for that particular cell in the case when they both flipping a coin, Fisher and Muriel Bristol? So basically the numbers, there are 8 in total. What are the chances of being in each cell here? So that amounts to really putting the numbers at random. So it means this is 1/4 here, 1/4 here, 1/4 here, 1/4 here. For that particular cell here, this is a binomial distribution, and we have a success rate of 1/4, and we're drawing 8. Okay, does that make sense for everybody? So because everything is just like counting sums, and there is one chance in 2 that this is this row, one chance in 2 that this is this column, so multiply both, it's 1/4. So the way I could resample this would be or binom, size equals 8, and then prob equals 1/4. And let's say n equals, I don't know, 100 or something like this. And so I'd get my numbers here in the top left corner. Nice. But we have said that this does not determine the rest anyway. Okay, so even if we knew this, we not really know the structure of the table. So we could say we count how often she's correct for this one, and that's our statistic. But that's not a very good statistic. We really get the feeling that we need to count all the cells from now on, because the structure of the table is no longer determined by just one cell. So before we do this, we need to study a little bit more the properties of the binomial distribution. And one thing that's quite interesting about it is that when the size increases, the distribution here, so we can increase the size to 1,000. Okay, the distribution here becomes smoother and smoother. And if I'm doing the histogram of that, quite rapidly here, it converges. Well, it's absolutely not visible here, so I'm going to say 10,000, and I'm going to put more breaks. Quite rapidly, it converges to a Gaussian. Okay, so a property of the binomial distribution is that when the size increases a little bit, already from 30 or something like this, then the distribution becomes kind of Gaussian. Of course, it cannot be a Gaussian strictly because it's discrete. The binomial distribution always remains discrete, but if you kind of excuse the discreteness of the distribution, you get something that converges to a Gaussian distribution. So what we can say is that here, what we have in that particular cell is a Gaussian distribution if the size increases. What we have in these other cells are also Gaussian distributions. Okay, does that make sense for you? Is that they're binomial anyway. If the size increases, then we can say they're Gaussian. All right. And now, how do we solve the issue that we need a statistic that does not take only this cell into account? So there was this study before, we can recycle it, which is we are going to take the squares of all the cells, basically, but not just their squares, the squares of their difference with the expectation. So that was the idea. That was still binomial question mark. I'm not sure what that refers to, Marco, your question. So we're going to compare the difference with the expectations, take the squares. So why do we do that? Because now we're taking the squares of Gaussians. And because we're going to make a sum of them, like 1, 2, 3, 4, then we're going to get something that has a distribution that we know. Does anyone remember from the video what's the distribution of the sum of squares of Gaussian variables? It's called the chi-square distribution. Right? That's the name of the distribution. And that's why the test is called the chi-square test. So we're going to just come back on the chi-square distribution for a minute to make sure that we understand how that works. So when I do, when I create a random sample here, with 100,000 examples in it. Okay. And if I want to now do the to see what they look like, I can use the function plot density. And density is kind of a nicer looking version of the histogram because it's smooth. Okay, so X was Gaussian, and then I get something that looks like a Gaussian. Depending on how you like your Gaussian, you can put it like this, but make it a little bit more flat, depending on what you consider as a Gaussian. But that's a pure Gaussian here. And what about the square of X? So I'm taking every Gaussian number, I'm squaring it, and I'm just plugging it into the density. What does it look like? It looks something like that. So it has a sharp peak for the small numbers here, and then it goes down like that. So what is this distribution here? So it's the chi-square distribution by definition. And what's the other name for the chi-square distribution? It's the gamma. The chi-square distribution is actually a gamma distribution. Gamma is a very general distribution. The chi-square distribution is one type of gamma distribution. So if I define now y as this calibrated distribution, so this is our gamma, for instance, and we say that we want the same amount, 100,000, and we're saying that we want shape equals something and scale equals something. Do you guys remember for the chi-square distribution what's shape and scale? Just 0.5 per degree of freedom, and we have 1 degree of freedom here. There's one Gaussian that we're summing, and scale is always 2. So I've got this, and then I'm adding it to the plot, lines y, and I'm putting color 3 for red. Wonderful, isn't it? Okay, so cat, take 2. Please remove this at the recording. Okay, so we're getting the distribution here. And what I meant, of course, is lines density. Oh boy. Okay, I hope this works now. Yes. Okay, so you've got the, it's exactly the same distribution, basically. So that's kind of the way we prove it. And we can also see that if I change the degrees of freedom, let's say 2 degrees of freedom, just to check, is it the same? I'm going to put it, I said red is 3, but that's green, of course, red is 2. You can see that 2 degrees of freedom is already a very different distribution, right? So that was really exactly 1 degree of freedom. There's no, there's no messing with the degrees of freedom. If you got the wrong ones, you got another distribution entirely. So basically, this part just shows that when you take a Gaussian, you square it, you get a chi-square. Now, if you take not just one Gaussian, you're going to take 4 Gaussians, okay? And then you square them, and then you sum them. So you make a sum of 4 squared Gaussian distribution. Let's see what we're going to get. So we need to work a little bit on our resampling strategy here. So we're saying we take 4 Gaussian numbers, we square them, we sum them. Okay, that's what we're going to do. And we're going to replicate that. Let's say 100,000, oh, it's not too long. So now X is taking 4 Gaussian random numbers, squaring them, summing them. And I do that 100,000 times. I hope it's not too long. Replicate is also not a crazy fast function. So I'm doing a relatively large resampling because I want the the density to be smooth. Sorry about this. Okay, so X is ready, and let's see what happens if I do now the density of X. I don't need to square it. The numbers have already been squared and summed. I got this distribution here, and if I compare it with the chi-square distribution with 1 degree of freedom, up, you can see that, yeah, this is not the same distribution. It's not the one with 1 degree of freedom. So I'm going to try 2 degrees of freedom, 3 and 4, etc. We're going to see if one of them is a particularly good fit. So this one is 2 degrees of freedom, not a good fit. Let's try 3 degrees of freedom. Oops, missed. Okay, not a good fit. Let's try 4 degrees of freedom. A bit of luck. It's going to work. And that's a perfect fit, near perfect fit. So when I take 4 Gaussian random samples, square them, sum them, then I get exactly the same distribution as a chi-square with 4 degrees of freedom, or the same as a gamma distribution with shape 4 divided by 2 and scale equals 2. That's exactly the same thing. So that's the point here, is that what I can do is, instead of taking that one cell as my statistic, I can, because I've got 4 Gaussians in the cells of the matrix, I can just take these 4 Gaussians, remove the expectation, I still get a Gaussian, square them, sum them, now I should get a chi-square. Right? Does that make sense for everybody? That this is a relatively long path just to getting to the idea that we're assuming that these things have a binomial distribution. They no longer have the hypergeometric distribution as we believed before. So we said it's binomial, fine. If the size is large enough, then it's going to be approximately Gaussian, fine. If we square this Gaussian and we sum them, we get a chi-square distribution. So we have, our score is fairly complex, but we have a way to compute its null distribution. It's always about being able to compute the null distribution. It's only about that. Okay? Does that go too fast, or you guys are following? Right? It's fine. So now we have a way to do this. The only slight difficulty, right, and that's something that's a little bit, how to say, it's a pain point in the chi-square distribution, is the fact that in reality these numbers are not independent. Right? So what is the thing? What is the constraint that links them? For instance, these 4 numbers. Exactly. So one very strong constraint is that they have to sum to 8. If you remove one somewhere, you have to add somewhere. Right? Like it can be in any of these 3 cells, but now these parameters are not independent. So you're not in the case that you have 4 independent Gaussian distributions, square them and sum them. That's not the case. You have 4 dependent Gaussian distributions, and that's why, in that case, you don't get 4 degrees of freedom, okay? Because it's not the same as summing 4 Gaussian distributions. So, for instance, how many cells do I need to fill before the rest of the matrix is determined? So we had said that when I only know this cell, it doesn't determine the other one. So how many cells do I need to know for sure to say, okay, the last one is that? You say 3. Okay, any other answer? Any person is different? Good, it is 3. Okay, so like if you decide of 3 cells here, yeah, exactly. So there are cases where you have 2 and their sum is already 8. In that case, yeah, okay, the other ones are 0, that's for sure. But other than that, other than corner case where the sum of these 2 cells that you define are already 8, then if you have 2, then there's still ways to pass the points between the remaining 2 cells that you haven't set. So in reality, you have only 3 independent Gaussian variables here, and that's why if we did the test with that score, we'd obtain a chi-square with 3 degrees of freedom, not 4. Okay, so far so good. All right, so that's the case of a chi-square distribution, which is not at all the one that most people do in the world. So why is that? It's because here we had this idea that Fisher was actually flipping a coin, and that Muriel Bristol was also flipping a coin. But in reality, why would they flip a coin? Why don't they have a random number generator, and then they say when this is 0.735, I'm serving milk first, and when it's more than 3.735, then I'm serving tea first. So why is it 1/2? And there's no reason for this, really. So when you get a real world problem, real world data here with numbers, and these numbers are from a process that you don't really know, and they look like that. For instance, 175 here, 394, 51, and let's say 213. You get something like that. Now, imagine that this is, again, they're playing the same game. They've been playing this game of tea first, milk first for many years, and then every time she comes for tea, this is like, you know, they do 10, 20, it's at run after 20 years. This is the way the scores look. And Fisher doesn't really tell us how he decided to serve milk first or tea first. And so you get something like that. Right. So now the question is, does that look reasonable to suppose that this is the flipping of a coin, heads or tail, that decides whether Fisher would serve tea first or milk first? And the question, does it look like Muriel Bristol is really flipping a coin to decide whether this is milk first or tea first? Not at all. Okay, the numbers are not at all in the realm of being close to 25 in each cell, and we've got no idea what's determining that process. So that's the typical case. You got a very, very general, very random contingency table, and you've got no idea what has generated this process, and you can really not assume that there is something with a probability of 1/2 that determines, you know, the state of whatever you're observing, tea first or milk first. So what do you do now? Any idea? First, how does that change the problem? The fact that we don't have a proper generation for what happened. And second, what's the solution? And this is a crucial part of the class. It's a hard problem. It's really a hard problem. So one thing is, what did we assume so far? What was this test for? It was the idea that the two variables that we look at are not correlated, that they have no association. And so we were saying here in that particular example, if Muriel Bristol has no superpower, then her answers are just, you know, they can be biased, you know, because maybe she thinks more often that this is milk first. So that's why, you know, she'd answer much more often milk first than tea first, because she has a proper bias, or she believes that Fisher does that more often, or something like this, you know, like she has her own biases here. But the thing is that we believe that there is no association between what she answers and what she served. In other words, we're saying that these two variables are independent. Okay, so we assume that these variables are independent. And so if they are, if we can show that they are, prove that they are is impossible, but if we can have an indication that the numbers are consistent with being independent, it says that Muriel Bristol has no information about what's going on. Okay, like whatever she served, it does not affect her answer. She is giving always the same answer, regardless what she served. Not the same answer, but the same probabilities of answer, regardless what she served. That's what it would mean. So in reality, what we're testing here is the null hypothesis is that these two variables, the way they're generated, we don't know it, no idea, but they are independent. They can have their biases, it's fine, but these biases are not correlated with each other. This is totally independent. So that's the way we're going to transform our null hypothesis. Fine. So what's the solution now? How do we generate the random data? How do we set the thresholds, etc.? How does that work? Just try, it's fine. We're among friends.
Getting the totals of each row and column.
Yeah.
Then to get the expected value, multiplying the two totals of that specific cell, and dividing it by the grand total.
Okay, so getting the expectation per cell. And how do you get these expectations per cell? How do you define them? Multiplying the totals, dividing by the grand total, right? So these expectations are based on the idea that the two variables are independent. So you say if 50% of the time Fisher serves milk first, and 80% of the time Muriel Bristol says tea first, then this cell here should be 50% of 80% of the total. So you multiply 50% by 80% by the total. And you just get their frequency as if there's really no information that's crossing between the two variables. Right, so that's what we mean by the expectations. Right, very good. Okay, so that's what the that's how this thing works. So we can then set the expectations here, and what is the distribution then of the number of individuals here in each cell based on these expectations? What's this distribution? It's binomial. Okay, like you say, we have this expectation that this is based on the grand totals, and then from that's the baseline, and according to the null hypothesis, then we are going left and right based on these numbers that we got from the expectation. And this is why it's really crucial to understand that this is probably what makes you feel that it's okay to do that sometimes, because that's what you do in the chi-square. Okay, like you're taking these magic numbers from the data. And I've said the one thing you're not allowed to do when you do a statistical test is to do that. So I understand now that it feels like, yeah, okay, I've been cheating all this time. Like the chi-square is this one case where you take the probabilities from the data. You were not able to come up with it before. That's what you said. This is not flipping a coin. So you actually cheated. You looked at the data, then you set your expectations based on that. Then you said this is a Gaussian distribution, etc. But you cheated all the same. You've taken these numbers from the data to get your expectations. And yeah, that's exactly the way it looks. But that's not what happens. Okay, that's really not what happens, but that's the way it looks. And the point of the tutorial of week 9 is to show you that this is not what happens, that this is not cheating. Okay, so why is that? It's because you need these expectations only to compute the statistic. Okay, we're going to compute the statistic in a second. But the point is that if we get a statistic that has a chi-square distribution, this chi-square distribution does not depend on the data at all. It's just a chi-square distribution, dots. There's no negotiation. This is just a chi-square distribution. So if we can show that the statistic we come up with, which is super complicated, does follow a chi-square distribution, by definition, this chi-square distribution is only one. There's only one given the number of degrees of freedom. So it cannot depend on the data. So the whole point of week 9 tutorial is to show you, to demonstrate as closely as possible to what is the case, that the only way we use the data is to compute that complicated score. It's not to set the expectations and then make a test from that. Okay, that's what we do if we were us. But these guys who made the test, they're geniuses. They realized that these are nuisance parameters, and they actually have managed to find a way to treat them as nuisance parameters, which is find the distribution of something that does not depend on these numbers. Like your score depends on this number, but its distribution does not. That's the whole point. So that's kind of the ultimate nerd case of nuisance parameters for statistics nerds, the chi-square. And I understand that this is confusing because it really looks like you're taking the data to get the expectations. Sure, call it expectations, but it's just to compute the score. So a lot of talking, but not a lot of statistics. So let's go. We're going to create the matrix here very rapidly. And so we said that this is 175, and then 213, and then 394, and finally 51. And for the matrix keyword here, and I say 2 columns. So my matrix looks like that. Okay, so here, what I want to do is to compute the expected values. So if I do a row sums of map, I got here 569 for the rows, for the first row, 264 for the second row. And if I do call sums of the map, then I get 388, 445. So now if I do the row sums divided by the sum of the map. So that's really the probabilities of being in the first row or in the second row, and the same for the columns. So these are the probabilities for the columns. So for example, the probability for that particular cell here, this is this number times this number times the total number of individuals in the matrix. That's 265 here instead of 175. That's the expectation. Okay, you see what I'm doing? I'm just counting what's the frequency of the first modality, what's the frequency of the first modality of the other variable, multiplying by the total. It's 265 here. So one cool way to do this is to use the outer product. So if I do the function outer of the row sums, the col sums, and I divide everything by sum mat, then I got already the expected numbers in each cell. So use that. That can be quite handy. Write it down or watch it on the recording for your tutorial. It's going to be quite handy. You don't have to do it, just that it will make your life easier if you can compute it this way. If you don't know what the outer product is, it doesn't matter. That's just like computing all the possible cross products. And so that's why it gives the proper results here. So I've got the the expected values here. So the chi-square distribution, how does that work? So that's what I'm going to call expect. EXPCT is that. So my expected values are here. The matrix is here. So if I do the matrix minus the expected values, oops, I get this. Okay. And if I square it, I get only positive numbers. And if I divide it by my expectations, now I get positive numbers, but that are no longer all equal with each other. And if I sum it all, I get my statistic, which is 180 in that case. All right, so that is, for those of you who have seen the chi-square test before, this is the way this is computed. Okay, you take the difference with the expectations, square it, divide each cell by expectation, sum it all, and then you get a number here. And it happens that this number is distributed according to a chi-square distribution. And it's got 1 degree of freedom, not 3. And this is a little bit of a mystery, and this is really hard for me to explain it because I don't fully understand it, to be honest. But the part that I understand why it's not 3. Why is it 1? That's still a bit of a mystery. So why is it not 3? Remember that when we said that here, in that particular case, we knew based on theory or based on what we wanted to test, that the expected numbers were 1/4 in each cell. Okay, so of course you'd get, based on this theoretical expectation of 1/4, you're going to get some deviations, a little bit higher, a little bit lower. But now, if instead of saying 1/4, I'm saying I'm taking as the expected value in the cell, not the theoretical value, but really the thing that I'm taking from the data, of course the deviations are going to be much smaller. Okay, like I'm kind of rescaling everything based on the data already. So I'm taking the mean from the data. So, obviously the deviation from the mean is going to be much smaller than the deviation from 1/4. The mean is taken from the data. So that's what kind of compresses the deviations of these 4 numbers that we take from the 4 cells. And that's what's removing degrees of freedom. That's pretty clear to me. What does it remove? Exactly 2 degrees of freedom? That I'm not sure. It does remove exactly 2 degrees of freedom. And so what you're going to see in the tutorial this week is this. You're going to go through the process of resampling that score, testing that this is indeed a chi-square test, and you're going to do this with a 2x2 table, but also with a bigger table, something that has 2x8, or you can do with whatever you like, actually. And so the process is always exactly the same. You always compute that score here, which is take the matrix, remove the expectation, square, divide by the expectation again, sum it all, you get a chi-square. So far, so good? Right, so this is an extremely confusing test. Because of this test, it looks like it's okay to take the data and make your null distribution from it, but it's not what happens in the chi-square. It's the way it looks, but this is not what happens. So as usual with R, there are ways to actually get the test directly. So all these things, yeah, of course. Why didn't you start with this? Like would be done already. So the way you use the chi-square test is fairly easy. You just plug in the data that you have, your contingency table. You can see that the p-value in that case is pretty small, and it tells you that the degree of freedom is 1. The statistic is not exactly the same as the one that I have. So it says a Pearson chi-square test with Yates this continuity correction. So it's not exactly the same statistic. If you want the same statistic as Pearson, not the one that has been modified by Yates, you need to say correct is false, incorrect. And then you get 180.64. You can see that this is the same score as the one that we had. Okay, so by default, when you use chi-square test, be careful that this is not giving you the original Pearson chi-square statistic. It's giving you a version that's slightly modified because it gives a faster approximation to the Gaussian. And so what's this continuity correction is the fact that the binomial distribution is discrete, remember? And so the quantile of the binomial are not exactly aligned with the quantiles of the Gaussian because of this discrete shift between 0 and 1, basically. So you just remove everything by 1/2, and then you get slightly better fit between the quantiles of the binomial and the quantile of the Gaussian. That's all. And you can see that the difference is fairly minimal here. It's very small. But still, if you want to use this chi-square statistic, you can compute it this way, which is relatively hard. The worst things, but it's not completely apparent. Another way, which is kind of nice, is just to say, give me the statistic here. So the nice thing about R is that you can get the statistic, the p-values, I think it's p dot value to get the p-value, etc. So there's plenty of interesting information, 10 to the minus 41, wow. Plenty of interesting information that you can extract in the statistical test, like statistic p-value. But if you extract the statistic using R, make sure that you say correct equals false when you want the original one of Pearson, which is the case for tutorial 9. Okay, so in tutorial 9, we're only working with the Pearson original version. We're not working with the modified version. So that's what you have to do in tutorial 9. I think you have a lot of information, like you've seen pretty much everything you need to be able to solve these problems. The rest is up to you on the concrete cases. But I think with this information, you will be able to understand everything and to run these examples that we've seen together, but on that particular data. In the few minutes that remain, I would just like to comment on the weakness of the chi-square test. There's one weakness, which is a pretty important weakness, is the fact that we have relied on the assumption that is coming from the the fact that the binomial becomes Gaussian. So when does that happen? In the case of the chi-square test, the convergence comes when the expected values are approximately 5 and more. So if when you compute the expected values in the 4 squares here, you get something that's way below 5, the Gaussian approximation is not so good, which means that then you don't really get a chi-square, which means that your p-values are off. Are you going to conclude, for instance, that this is not significant when it is actually very significant, and vice versa? It's just that your distribution becomes unknown. Yes?
Isn't it usually when the sample is bigger than 30? Central limit theorem?
Yeah, exactly. For the central limit theorem, you say it's Gaussian when the sample is bigger than 30, then the mean becomes Gaussian. But here, this is not exactly what happens. We have a convergence of a binomial, and we want the chi-square to be good. And you need to look at the details. But basically, the one thing that plays more is not the size of the cells; it's the way we compute the expectations. And the way we compute the expectations is also what removes the degrees of freedom, by the way. So that's really what counts more. It just happens to be this way, but otherwise you're 100% right. So that's a test that doesn't work very well for smallish samples, for smallish expectations. And so that has led to plenty of of hacks where you just merge categories together, etc., to get expected values that are above 5. A little bit ugly. The Fisher test doesn't have this problem. It's an exact test. Fisher computed all the possibilities for fitting the tables, but you have to understand that the Fisher test does not make the same assumptions at all as the chi-square test. They're not exchangeable. Okay, when you have a 2x2 table, you cannot either do a chi-square test or a Fisher test. Either you resample with replacement or without replacement, and that depends on what you believe has happened. It's not based on like, oh, I really like the Fisher test or something like this. Okay, like you have the choice between these two tests, but only one applies for any of the situations. And sometimes you see, oh, the samples are too small, I cannot do a chi-square, so I'm going to do a Fisher test. It's not the argument. The argument is, how was the data generated? Is it the case where kind of people knew that there would be only 4 of each, etc., or did they not? That's what makes the difference. Fisher is without replacement and chi-square is with replacement. So either use the binomial distribution or the hypergeometric distribution. All right, that's it for today. It's already time, so thank you very much. Good luck for the tutorial and see you soon.